Let's take a look at a slightly more complicated example here. We've got an integral of e to the x minus e to the negative x over e to the x plus e to the negative x all squared. There seem to be blocks that would make sense as substitutions, either the numerator or the denominators inside. And just ask yourself for a moment, which one of these do you think will be the substitution that leads to a simpler answer? Okay. If it's not entirely clear, that's fine. We're going to take a look actually at both ways, both possible substitutions, and see how they transform the integral, and hopefully in a way that'll make it clear in the future which substitutions are more likely to work or be helpful. Let's take a look where we pick w to be the numerator here. As soon as we do that, our dw dx is the derivative of this, which is e to the x minus e to the negative x times negative 1, derivative of the exponent, or e to the x plus e to the negative x. What that gives us is a relationship, again, between dw would be 1 over e to the x plus e to the negative x. That would equal dx. We bring the dx up, we bring this whole term back down, and we get that ratio. If we were to do that, then we could rewrite our integral. Our integral, this one up top here, we just set w equal to the numerator, so we'd have the integral of w on top. The bottom is not w, so we leave it around. Whoops, there should be a squared here, my apologies. E to the x plus e to the negative x, all squared, times, now here's this relationship. Dx, the final factor in our integral, is going to be dw times 1 over e to the x plus e to the negative x times dw. And here we ask ourselves, is this simpler? And are there no x's? And I think in this particular case we have to say no, this is not simpler, and no, it does not have the x's gone. We in fact have this complicated product in the bottom. Maybe there's a way to make w and the e's work out, but it's certainly not obvious. That would be my first guide to say, let's rethink our original substitution w. Let's try it with this being the power in the denominator, or the inside function of the denominator. If we do it with dw dx here, we're going to get the derivative as e to the x plus e to the negative x's derivative, that'll be minus e to the minus x, or 1 over e to the x minus e to the minus x equals dx. Again, bring the dx up, bring this down, and we'll need a dw in there. My apologies. So that will be our reconfigured relationship between dx and dw, and that means our integral, I won't write it out in full for space reasons, but at this integral we can rewrite it as w is the e plus e minus x. That's not the numerator, so we keep the numerator. The denominator is w, and it was all that squared, so I'll have w squared. And then, what's left? Oh, right. Original integral, we've done that. We've done the denominator. Now the dx. The dx is equal to that dw with the exponentials in the denominator. And there we see the payoff. Now we can cancel things and get the integral of 1 over w squared dw. We ask ourselves, is that simpler? Does it have no x's? And the answer, of course, in both cases is yes and yes. Let's write that legibly. Simpler. This integral is far simpler than what we started with, and it's actually so simple we can actually integrate it right away. We'll write it as a power to make the power rule easier to work with. w to the negative 2's integral is w to the negative 1 over negative 1. Add 1 to the power, divide by the new power, plus a constant. And that will be negative 1 over w, which is e to the x, plus e to the negative x. All of that plus a constant. So looking for themes again, what do we get to do as part of our substitution? We get to divide by, notice what we got here, we got to divide by the derivative of w. We wanted to divide by the numerator to get it to cancel. There was no sense dividing by the denominator because then we got more denominator than we started with, and we were never able to get rid of the x's.